Hello, welcome to Security, Cryptography, whatever. I'm Deirdre.
I'm David.
I'm Thomas.
And I'm Colm.
Yay! Tom's our special guest today. I'm a cryptography engineer at the Zcash Foundation.
I am a engineer at a company called NameTag, but I also did a PhD in almost cryptography at Michigan and co-founded Census.
Cool.
I'm an engineer at Fly.io, and I have 1 semester of undergrad college.
I'm an engineer at Amazon Web Services, where I work on security, cryptography, identity, and virtualization.
This is very exciting.
You're one of the coveted principal engineers at Amazon, correct?
Yes, I'm definitely a member of the Amazon principal engineer community.
Cool.
It's fun.
Welcome, Colm.
What is that?
So at Amazon, you know, when you join as an engineer, typically you come in as an ST1, right, which is typically a college hire, and then ST2 is our next level at that. After that, it's kind of still kind of an early career position where people learn how to be really great software developers. Then ST3s are lead developers, and then after that, you become this, you know, blessed principal engineer who you know, supposedly we are great at, you know, stewarding and shepherding projects across teams and across the company and figuring out what the technical direction should be, as well as getting real things done.
Does it come with powers?
It comes with a title. It doesn't. There's no intrinsic powers. It comes with responsibilities. I found out the hard way that, you know, tends to make things harder rather than easier.
But do you have minions?
I do not have minions. No, I work with a lot of teams, and I have to help a lot of engineers, but none of them just do my bidding. Everybody always wants to argue and figure out what the right thing to do is.
How much bar raising do you do per day?
All the time, everything. It's a constant bar raising. It's more of a life philosophy than anything else, you know.
I gave a talk at Amazon like a bunch of years ago about, like, I think it was our cryptography for pen testers presentation that we had done, like, at a bunch of places. And when I was there, like, it was like a blue hat kind of thing where they had outside people from a bunch of places just presenting to the Amazon team. And like a bunch of people at Amazon, like the engineers there, were talking about how they would get like sponsorships or recommendations from people outside the company. Like, that was a strange Amazon culture thing I was unaware of. At least at the time, there was some process where, like, it mattered if somebody outside of Amazon like wrote you a recommendation or said something nice about you. Do you have any recollection of that? Am I crazy?
You're not crazy. It's definitely something that comes up. We do, you know, when people are doing annual review processes or promotion processes and all that kind of stuff, it's not that unusual to look for feedback from folks who don't work at Amazon, in part because, you know, we try to be really customer obsessed, and getting feedback from customers is super valuable, but also partners and vendors and other people we work with, because, you know, their feedback's really useful.
This reminds me of the tenure process. When you're going up for tenure, and if you're in academia, you have to get letters from people outside your department or, you know, outside your school, who could be like, yeah, I would totally give them tenure or whatever, but I'm somewhere else. So, yeah.
Yeah, and I think when part of someone's role is, you know, interacting with the industry, it becomes particularly important. I can definitely think of some people like that's most of their jobs.
Yeah.
So they probably have all sorts of feedback and recommendations like that.
I just want to tell people working at Amazon that I am available for recommendations and that my fees are very reasonable.
Do we want to talk about S2N, like the AWS cryptographic library?
Sure. Amazon S2N, it's an open source project. It's on GitHub. In our you can find it there in our AWS repo, and it's short for signal to noise, which I'm amazed was a name that was left there in terms of for a cryptographic library, how no one had taken that name before us. You know, because the core function of cryptography is to turn meaningful signals into useless noise, right? And to hide information in plain sight. But it started as a library that just implemented TLS, right, and SSL, and we would use, you know, OpenSSL's libcrypto or other libcryptos under the hood to do the core cryptography. But steadily, bit by bit, we're kind of taking on more and even implementing that. We've got our own libcrypto project as well that kind of plugs into it, and we've grown to support Quick and some other stuff in there. We've got some cryptographic primitives that we use in non-TLS contexts as well. That's all part of S2N. And I think it's been going 6 or 7 years now. I can't remember.
I'm trying to remember what was going on with TLS 6 or 7 years ago. Like, what was the impetus for starting your own TLS implementation?
Yeah, well,
Something other than OpenSSL.
So development on S2N started literally the day after Heartbleed, just to get directly at that. So that was definitely a trigger. But we had talked about and discussed our own internal need for S2N before that. And we had actually outlined it, and we were planning on starting it probably about 6 months later than we did. Because we saw there were like some performance optimizations that were kind of on the table. And we saw that we just had to get into this game of owning this part of the stack ourselves for a bunch of reasons. But when Heartbleed happened, it definitely accelerated my timeline. I literally started working on it pretty much full time right after that. Not quite S2N itself first. The first thing we wrote was actually a kernel module that would act as a network filter that could block Heartbleed, because we had some customers stranded who couldn't update their copies of OpenSSL. So we wrote a little module they could use on their instances. And then that kind of grew to become S2N.
So they couldn't upgrade OpenSSL, but they could install a kernel module?
Yeah, so we had a bunch of customers who were kind of in unusual situations. Some we were able to help them with hot patching, right? So Heartbleed was a pretty easy issue to hot patch binaries for. Literally just find a block of code near that processes these heartbeat requests and add a jump, and then add a section at the end of the jump that adds a condition to defend against Heartbleed, and then jump back to where you went, right? It's actually not that hard to do. But we had some customers who had validated binaries that they couldn't change. They had self checks and checksums that have to pass, and so you couldn't modify the applications themselves. So you can't hot patch it. So now you got to do something in the network, and that meant shadowing and parsing the entire kind of SSL TLS state machine, detecting a heartbeat record and rejecting it. So that's what we did.
Is that code still alive, deployed somewhere?
I hope not. The module is still public. It's in my GitHub repository, but it's I hope nobody's still running that. That was definitely intended as a band-aid to help some people get by who didn't really have any other option.
I'm looking at the introduction for S2N, the your announcement post, how it played on Hacker News in 2015, because that's my lens for how to look at everything.
Yes.
And the top comment there is about a 12,000 line OCaml implementation of TLS. And my question for you is, why did you not implement it in OCaml?
Well, I personally am not OCaml literate, and so I implemented it in C. And I guess the other big reason to implement it in C at the time is pretty much everywhere we did TLS, every application that did the front end SSL TLS processing, it was also written in C.
Yeah.
And so we didn't want to be constrained. And we had some, compilation target environments that couldn't even compile C++ to. So so we were pretty restricted. We were able to get to C99. But pretty much even our embedded environments could support that. But that was pretty much our lowest common denominator at the time. Wasn't what I do today, but that's what we did at the time.
What kind of embedded environments are these? Clients talking to AWS or something else?
Well, so as the name is, it's Amazon S2N, and it's not just used in AWS.
Yeah.
And in fact, at the time when we wrote it, some of the smallest compilation targets included things like dash buttons, which are I don't know if you remember those, right? So, think about trying to get a TLS stack that can run an environment like that.
Got it. All right.
Very, very small, very tiny footprint.
Oh, so there's like a little section of post-quantum crypto in the S2N repo. Are you deploying post-quantum crypto to dash buttons? Please say yes. Please say yes.
No, I don't think so. As fun as
Can
that would be.
you still buy dash buttons? Are those still a thing that exists?
I know that they still work, and I know that I know that they could still be used. And I actually have a friend, and one of my friends, she works on S2N and she has dash buttons, and they definitely still work.
Oh my
But
god.
I don't know if you can still buy them.
Huh.
This is like the thing where if you're out of detergent, you just have a button next to your
Yes.
washing machine, and you push it, and then detergent comes.
Yes.
Yeah, they're really cool.
They are really cool.
Yeah, I actually got one that just every time I hit it, I get a new TLS notification.
Yeah, it's now you can just ask your Echo device to do it for you, and you don't even have to press the button. So,
It's a good
but
point.
it's
So like, there's like the Heartbleed happens. So I guess you announced S10 in 2015, but Heartbleed was like years before that, right? But like, you have a sense of where like OpenSSL is now, but you also have a sense of where it was back then, right? Like, I get it's easy to sell me an S10 in 2012 or whatever, right? Like in the bad old days of OpenSSL, right? But like, if you were going to make a sales pitch right now for like use this different C implementation of TLS instead of OpenSSL, I believe that there's a good pitch there. I'm just wondering what it is.
yeah. Well, first, I don't mean to criticize OpenSSL, and don't ever take anything I'm saying. I think OpenSSL is probably one of the greatest world goods that has ever achieved in software development. Literally, like a mostly volunteer team that brought cryptography to the masses. It's just an amazing accomplishment, and I don't ever want to talk that down. I've also pretty good friends with a lot of the OpenSSL team, so I don't want to get in trouble with them.
We all agree, which frees us to be mean to it.
Okay.
Yeah, and what we can, I was gonna say, we can put in the standard disclaimer now too that like OpenSSL in 2014 and OpenSSL like now are
They're
also two
miles
very different
apart,
beasts.
yeah.
I also wouldn't, in OpenSSL 2014, I wouldn't go like beat anyone with a stick because of Heartbleed. I think there's a lot of things that kind of led to that happening.
Yeah.
But
Because good.
it's certainly what you're talking about when you're creating S2N then is not at all what OpenSSL is like now.
Yeah, good context setting. So the big motivation for us was really to have fewer security issues to deal with. And there's two senses of that, right? One sense is, well, we really do have to have a lower risk profile. There are, sometimes bad actors coming after our customers, and we got to be able to protect them, and there's some real threats there. But the other level of it is, no matter what, anytime an issue comes out, no matter how low the risk is, you got to go do a bunch of updates. And those can be pretty disruptive. At Amazon scale, rolling out a software update in a low-level library or a low-level system, like SSL and TLS is used everywhere, like can cause, a lot of teams to have to pause. And then they, don't work on their own roadmap for a bit. They go and pivot, and they have to do this update and get it deployed and do all their testing and so on and so forth. And I don't know a good way to measure the impact of that, but it is certainly tens of millions of dollars, like at Amazon scale, right? It's like just a huge, over many years, the amount of whatever that productivity loss is. And the development cost of something like S2N is always going to be less than that. And as long as we can do it in a way where we add the right, defenses in depth and have a much more minimal surface area, the advantage is you got to just sit there and write out all those updates. And that's pretty much worked. There's a lot of updates or issues have come, and we just didn't have to do anything at all. And all of that productivity is saved. And that's the main benefit. And that was the main pitch. And that's how we kind of continue to go at it. Then secondly, the performance. There's performance enhancements that are still on the table. We still have ideas for how we think we can do pretty serious performance savings in how this stuff works. And we got some pretty big wins. When you're looking at a system like Amazon S3, even like 2-3% performance improvements turn into, big numbers very fast.
Yeah. Especially when you're like the first stop for a cache for anything for the internet, just stick it in S3. So any of that, when you're effectively a cache for the internet, any of that latency is felt, including in your SSL handshakes or whatever.
I guess I should have asked like a second ago, but like, where does S2N live in the architecture right now? Like literally everywhere in AWS where there would be a TLS, is it now S2N?
Not quite everywhere. There's a few left. We're very, very careful about how we update and making sure we don't break customers and we preserve backwards compatibility along the way. But pretty much if you talk to an Amazon Web Service, if you call it API, that's S2N. If you hit the CloudFront CDN, that's S2N. If you hit Amazon S3, that's S2N. If you hit network load balancers, that's S2N. If you hit an application load balancer, it might not be S2N. That's one of the few things that's left on our list, but we're working on that one.
Nice.
And that'll be fun.
So in terms of the productivity kind of gains, is that coming because you have to patch less or because you can patch easier? Because it's like within your build system and owned by you.
Yeah, I think the answer is yes. And it's mostly having to do nothing. You know, it's nice to be able to say, well, this issue came in, but we don't have to worry about it. We just don't have to do anything. That is by far the biggest win. And then because it is in our development and build system, and it's kind of a first class project internally, you know, that is easier. It's also, you know, if there is an issue with S2N, right? If there is a security issue with S2N, we're generally, you know, going to be where any security researcher reports it to, right? So we're going to have kind of firsthand privileges in the embargo process, right? And be able to coordinate with them and have everything updated. And the day customers find out about it, everything's already patched, you know? So that's a good productivity win too.
That's an interesting way to be like, is there a value to a quote unquote fully open source project like OpenSSL that's available to quote anyone, but that means that it's also controlled by no one in particular, so everyone has to coordinate and you're at the whim of the project and you have to try and get your fixes in line. And if you're at Amazon, you're just like, well, no, that I can't work in that workflow. I'm just going to go over here and do it on my own. So I guess the value would be to smaller organizations than an Amazon or an AWS or
yeah,
Google.
I mean, for us, we maintain a full Linux distribution too, Amazon Linux. And so we already have to patch everything, you know, well within embargo timelines. And we have to be able to do that. And so we put a lot of work into being able to respond to any issues that are reported in any kind of project, you know, very, very, very quickly. But that is a hard thing for a small organization. I can't even imagine.
Yeah. You have a whole Linux? I forgot.
Like, I guess, like, I feel like I know the answer already, but I'll ask anyways, right? Like, if I was to come at you as, like, the skeptic saying, I simply don't trust memory unsafe C software. Like, what is the set of things that you guys have done? And I know there's a bunch of things you guys have done to mitigate that concern.
Yeah. So, well, firstly, I'd point out that almost every memory safe language, especially the dynamic ones that you can think of, is itself written in C at some level. You know, we have exceptions now that are able to be self-hosting, but you know, at the time, even if you thought about the JVM or you know, huge things like that, and so there's no like magic that they have access to that you can't also do in a C program. So we essentially wrote in our own dialect of C, like a pretty restricted dialect of C that takes its inspiration from functional programming techniques. And so we structure all of our memory handling and I/O through a very kind of functionally inspired architecture, you know, called stuffers, where we create these, you know, which is like a buffer for stuff, right? And it's really, really simple. It's a very simple data structure that keeps a cursor, right? And anytime you write to it, increments the cursor, and anytime you read from it, make sure you don't read past the cursor. But when you use a technique like that and you write code like that, it makes everything like beautiful and declarative looking and very functional seeming, right? We did another example of that in how we constructed our state machine, where literally we're using like a fixed, you know, table of function pointers, and all you do is increment your way through the table. And so it's kind of writing C like you'd write Lisp. So maybe your OCaml question wasn't so crazy. And then we did, you know, just an enormous degree of testing and verification, all the way up to formal validation.
Oh, I've heard about that, yeah. So it sounds like the answer is you have to write your own variant of C to do this securely.
I don't know you have to, but it's what we did. It's I always think of, your starting point is that the first layer of defense is always going to be writing the code and whoever's reviewing the code, and you have to make that as mentally untaxing as possible. And
Yes.
you have to make things as consistent and idiomatic as possible, so that anything unusual will really stand out. And for me, that means you probably want to go for a pretty restricted small set of patterns that you're going to program with and use, and start there.
Yeah.
And then make tests easy to write, and have lots and lots and lots of testing and test cases. And then do fuzzing, because fuzzing is really, really awesome. And then after you've done all those things, if you can spare to think about doing some formal validation as well.
What is the formal validation story there? What are you guys doing there?
Well, we formally validate quite a bit of S2N. We do things like we formally validated our state machine, that it can't get into any invalid states that aren't allowed by the TLS specification. We formally validated our memory safety by doing some processes. We have a tool called CBMC that we run on like our core stuffer and IO algorithms and all that stuff, and we validate that that's always going to be correct no matter what the input is.
Nice.
We formally validate our implementation of HMAC.
Cool. Yeah, I remember this. Yeah.
That was fun, because we wanted to see if we were getting better at formally validating things, because about 2 years prior there'd been another formal proof of a different HMAC implementation. And we wanted to see if we could make it easier. And we formally validated a bunch of our algorithms, more and most of the post-quantum ones that we're working on as well.
You have formally validated them?
So
like bike and psych?
We are formally validating those.
Cool.
I think those algorithms aren't yet like locked in to the point you can even say that they're validated, right? They're still open to tweaks on various parameters.
A little bit.
You're validating that the implementation matches the algorithm, or that some property about the algorithm itself.
Yeah. So most of our validation, what we do is we validate that the actual compiled like machine code matches some simple specification, like declarative specification of a protocol or a safety property, some kind of set of invariants that we want to be able to hold it to. But we try to go all the way to the machine code where we can.
Got it.
I'm Googling right now, like formal verification and S2N, and like Galois comes up.
Yep. Yep.
Like, I'm gonna nerd out a little bit here, right? But I'm just curious about like what the tooling looked like and what those projects look like.
Yeah, so Galois was one of the companies we partnered with super early. Actually, not long after we started S2N, we had Byron Cook join AWS, who's now a distinguished scientist at Amazon. Cool. And he's an awesome guy, real leader in the field on formal verification. And he connected us with Galois so we could get going before he was able to hire a full team. And we still work with Galois. They're awesome. And they have these tools called Cryptol and SAW that are they're specifically designed for verifying cryptographic code and cryptographic algorithms, which can be, some traditional verification tools from like the safety critical world don't really apply, because there's so much entropy and randomness in cryptography, and you have to be able to kind of abstract that out. They were able to come up with, Cryptol and SAW specifications for the HMAC algorithm and for the core TLS state machine. And they were able to find issues. It was really cool. They actually found that there were certain like invalid combinations of TLS extensions that could cause us to abort the TLS state machine early. Now, it wasn't a security issue, but it was still pretty good find. I can't think of any other way we would have found that.
So is that the specification allows this? You can be conformant with TLS like 1.3 or whatever, and you have all these extensions, and that is allowed by the spec. But if you implemented the spec as written, it would get into this weird state that you really should not be allowed to be in.
Kind of. It was so TLS has supports session resumption. in its state machine, right? So normally when you connect to something over SSL, there's a handshake and there's a bit of a back and forth, and you eventually negotiate a key and then you encrypt stuff over it, right?
Yeah.
But you can skip most of the handshake by doing resumption.
Yes.
And what they found was if you showed up with this weird combination of extensions in which you shouldn't resume, it could try to resume, and then the resumption would fail. What it should do is just carry on and do a full normal handshake. But it instead tried to resume, didn't resume, and kind of gave up and aborted the handshake early when it shouldn't. That was the issue they found, which would be really hard to find.
So did that result? That sounds like a section needs to be added under session resumption in the TLS 1.3 spec to be like, well, make sure that if you're, blah, 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 blah. So did anything get updated after you found this?
So that was on the state machine that's part of, SSL v3, TLS 1.0, 1.1.1.2. The TLS 1.3 handshake is radically simplified.
Okay.
And,
all right.
And does not suffer from any issues like that. There's just nowhere near as much kind of parameterization of the TLS handshake in 1.3. It's way, way simpler. And that was inspired by issues like that GOA found.
That's awesome.
And the 1.3 handshake or specification itself has been symbolically formally verified.
I think so.
The spec doesn't have invalid states with Tamar.
Yeah.
Having been through the process of taking a relatively complicated state machine like TLS and then seeing it formally verified, and you're a software developer like the rest of us, right? Like, are you still comfortable building state machines, building protocols, like just building software without formal verification? Like, I have friends that do this and they never come out from behind the looking glass. They're just permanently like formal verification people, and from that point on they just don't take seriously anything that isn't formally verified. Have you fully drunk the Kool-Aid on that now?
Maybe not fully. So what I'd say is, first, if you have to build a state machine, right? And if first rule is in your code, in your functions, do not mix input parsing and changing states, right?
Okay.
Don't mix those core things. Separate those really clearly. Try to have a set of code that really clearly describes how you're going to go through your states, and have that very separate from the code that's going to parse input and do stuff like that. A lot of projects, they're a mix of those things. There's these huge big functions that do both, and it gets just too confusing and gets too spaghetti-like and is unreviewable, in my opinion. So you first got to do that. That's the biggest thing, and that structure helps. The second thing then I tell people to do is linearize all your possible state transitions, right? Okay. So instead of having conditions in your code that can go, well, if this happens, then jump to this state, and so on and so forth. Instead, lay it all out in these linearized tables of well, this is one valid set of state transitions in one table. This is another valid set of transitions in another table. If you have too many tables, if that feels like you won't be able to program that, give up and redesign the state machine. That's a big hit that, you're too flexible in all your state transitions. Mm-hmm. And if you do, and those two things I think matter more and probably prevented more issues and bugs for us. And then, formal validation after that kind of gets you to 100%. It's you do those things, you'll get to 80, 90%. But, formal validation is probably the only way you're going to get to 100%.
This gives me a little more confidence about doing Zcash stuff with the network and the this and that in Rust. And we are doing as you described. We have parsing over here and it throws errors if it doesn't do anything it doesn't understand. We have state transitions and how we handle them over here. But also, shout out to Rust. There's the type safety in Rust makes it very easy to encode states as EDM variants or types, and to say you can only go from one state into another valid state. You cannot go from any to any, or from valid to invalid or something like that. And you can check it at compile time, and it's very nice for that sort of thing. So.
Big fan too.
You can use S to N with Rust, right? There's bindings.
Yeah, there are bindings. You can use S to N for most time. We do. We have various Rust projects that use S to N, including the new Rust SDK for AWS. And we go the other way. There are now parts of S2N that we're writing in Rust. Like our quick implementation is written in Rust because we feel like it's ready and it's a better starting point for all that.
That's so exciting.
What are the prospects for Rust fully infecting the S2N project and you gradually hoisting out most of the C code?
Not imminent. In general, we try to leave code that's working alone and not go rattle it. But I mean, I'd love to see it all.
That's what the OpenSSL people said in
what, 2014.
Well, I mean, they could say it now and it's much more credible because like lots of stuff has happened. But
yeah, I mean, it'd be great to see it someday, but we don't have any imminent plans.
Yeah. I meant to ask, does AWS have a fuzzing cluster, or are you leveraging open fuzz or whatever it's called?
So we do. So at Amazon, those kind of practices are kind of up to each team and what they want to do. But we do have some centralized fuzzing infrastructure, and we do have a compute cloud. It's called EC2.
Yes, I might have heard of it.
It's got some compute. It's got a few instances we can use now and then.
Cool.
And we certainly do use it. I mean, we've been fuzzing on S2N it's been running for years and years and years
Cool.
at this point.
Awesome. Did you write your own management to run and report and correlate, or are you deploying? Because I tried to deploy whatever there's a cluster fuzz, OSS fuzz, the Google run one. They have a piece of software that's like, Kubernetes. Here is how you have a web app that deploys your fuzzing infrastructure, and then you can tie it back to your repository or whatever it is. Do you have something like that?
Well, the first fuzzing tool that I wrote, I just used Elastic MapReduce, and kind of like threw it at it that way. I've seen us use Lambda for it as well.
Really?
Just as a nice, cool demo. I think Lambda's cool for fuzzing. Obviously, you can't run things for very long, but it's still useful for integrating it directly into the build process if you want to get just a really, really quick yes, no on something. And we do that sometimes because it's not feasible to run it on everybody's desktop for that kind of stuff. But I don't know, actually. I should ask the team how they're coordinating and running it these days.
Yeah.
There's a lot of different ways to run something in parallel across many EC2 instances.
Yeah, but like specifically a lot of people will write a fuzzer and then they're just like, run the fuzzer for, I don't know, some amount of time as part of their CI or CD or something like that. And then, you're not really getting the real benefit of fuzzing. You need like a continuously running fuzzing infrastructure. And then you also need it to report when it does something, and then you have to correlate it back with the change that actually that you found the thing on. And all of that work, not just the like deploying lots of compute in parallel, turns out to be only one solved problem, at least as I've seen. Actually, that's not true. There's cluster fuzz if you run it yourself. Someone took cluster fuzz and they were trying to run it as like a service, they basically OSS, open source fuzz, but like pay them to do it well for you. And I think they shut down or something like that, and it made me very sad. So if you have software that makes this task easier for people to do, or the people who have it, I am interested and I would like to see more of it in the world, please.
Sure. I'll ask them. Maybe we should have a service for it. I always view the stuff that's integrated right into your CI pipeline is really just to give the developer feedback that they haven't broken the fuzzing infrastructure.
Yeah, but you want to auto deploy anything you've changed with to like your fuzzing infrastructure or whatever. So either way, but enough about S2N. Tell us about mTLS.
Oh, wow.
I would just like I would actually I'll put something in the middle there, right? Which is just like you've now had the experience of being like firsthand to a ground up implementation of TLS. I think I bring this up every time this subject comes up, right? But like one of my favorite people is Watson Ladd, and Watson Ladd had like a comment that has stuck with me forever on the CFRG mailing list, which is the IETF crypto review board, where he compared TLS to like an undergraduate like secure transport, like undergraduate homework assignment, and said that you would have gotten a C on it if you had turned it in. What's your general take on TLS at this point?
I think it takes all sorts of internet standards are like that, right? And you can't be too hard on them because, a lot of them came about through a culture of experimentation and iteration, right? And then sometimes something takes off and succeeds wildly before maybe people got another chance to iterate, and then you're all stuck with it because, it's just baked into everything. One of my favorite examples of that is actually like TCP and UDP, like even like way back, like UDP has this crazy design error where it does fragmentation at the IP layer, right? Like the header in a UDP packet is only in the first packet, of a fragmented datagram, which you would not believe the amount of extra money that makes routers and switches cost. Right? Because they have to be able to like reassemble those packets and so on to be able to do flow switching, right? And you would look at that and you go, well, you'd get a C- on that design. It would have been trivial to just put the UDP header in every packet, right? But you can't see it like that. It solved the problem and it did it really well and took off. And TLS is the same. I mean, you can look at it and say, "Oh my God, look, they got the Diffie Hellman exchange the wrong way around." I mean, this is clearly a C-, but they built a really cool protocol that could effectively emulate TCP enough that you could just bolt on existing protocols and get going, And it's a good example of an MVP succeeding. And maybe we got better. We have to get better at iterating, and it shouldn't take 20 years before we're able to like all come back and let's hammer out a better, more optimal design. So I kind of see it like that.
I feel like there's a point where you warned me about the UDP fragmentation thing. We did like an all BPF implementation of UDP for Fly. And like, you were like, UDP fragmentation, and you didn't use these words because you don't use words like this, but you were like, UDP fragmentation is going to screw you with like DNSSEC. And I'm like, oh, it's going to screw up DNSSEC. Oh no. And then I've moved on. It's only
Cats
because you
do
mentioned
that.
it. Only because you mentioned it now do I remember that you warned me about that. But so like, I guess like part of the reason we're bringing mTLS up is like, there's like a sort of brave new world of how like people say microservices, and I hate that term, but like modern application service ensembles. That's MACE. That's my new acronym. Anyways, for these MACE applications, right? Like there's this notion that like you've got all these services running now delivering the same application. They all talk to each other, right? And like we now have an opportunity to use TLS to secure the connections between those services, right? Mm-hmm. Like you've got all these random things talking to each other, and like in the bad old days, there'd be no good way to kind of authorize who's allowed to talk to what. It's all just kind of like you'd run TCP dump to see what's going on. And now what we can do instead is like bolt a proxy onto everything and have it talk mTLS. And like mTLS is the way that you would like TLS, the TLS protocol that we're talking about, right? But in mutual mode, where you're presenting both client and server certificates for things, right? And if you look at that, like you can get a long ways, into the kind of the authorization and authentication problem. You can get a long way solving those problems just by using certificates and both sides of TLS, right? And that's essentially, it's kind of where Kubernetes is going, right? It's towards something that looks like that. And I gather you're a great fan of this.
I am not. And I think when I first saw the designs from like Istio and Spiffy and so on, I sent them a very long note with like my 56-point detailed critique of why you really don't want to use mTLS for this. But at the same time, they're solving a problem, right? And they're plugging into a layer that they can. But I'll try to give some more detail. I have a long history with mTLS. When I was still in college, one of the ways I was kind of paying the bills, I was a member of the Apache HTTP project, right?
Oh.
Writing code for the Apache web server. And at that time, it was still mostly non-US folks who were working on the SSL stuff because of, silly crypto export restrictions and so on. And so, I would help people with the SSL stuff, and I would help developers with them, and I would help, people who are just running Apache with them. And I would do these workshops, and through that got into this kind of business of being an amateur auditor of people's mTLS setups. They would come to me or through somebody else at Apache, say, can you take a look at this and see if we've actually done it securely? And first, I was not a professional security auditor or reviewer or anything even resembling that. So the fact that they were like coming to me, and I was, pretty close to maybe one of the best people out there to do that, was a really bad sign that this was not a very mature, ecosystem. And literally in every single case I looked at would find unbelievably low-hanging issues, like stuff that it just didn't work at all. And on top of that, it was, it's a really complex ecosystem. When you're using mTLS, there's a lot of X509 flying around, a lot of string parsing flying around. And like I was saying earlier, like you're going to have to respond and update to a lot of security issues when you bake that really deep into your stack.
Right.
And that's going to slow you down. But like just some of the top things, literally revocation, almost never had they built a working revocation system. And I kind of think about, when people tell me you should back up your data, I'm like, the first question I'm asking is, well, but how do I restore it? Like, that's the important part, right? And when somebody tells me you got to be able to rotate your passwords, I'm like, I don't really care about rotating them. I want to know how you revoke them. Like, and tell me, how do you make sure something can't be used again? And they would just, almost everyone would like, well, we'll build that later. Or, they would use CRLs or some huge list. And then I'd ask them, well, what if you have to revoke everything? Like, is that going to scale? And they just never really have an answer, and it was kind of scary. And then I would find these cases where authentication wasn't happening at all. People couldn't tell. Like they were using the system, they were going to some intranet sites in their web browser, and everything worked, but under the hood, the client certificates weren't even being used. They were just getting regular TLS, or so there was no easy way to tell. And I found cases where people were doing authentication just based on the strings that are in X509. My favorite example of that was one of the first projects I did. We found that the CTO's EA, right, his executive assistant, could pretty much do anything she wanted, and like she had god level power in the system. And at the time, I thought it was, well, we must have put her in the CTO's group, and the CTO's group has root power, and so that makes sense. We'll track it down and figure it out. But it wasn't quite that. It was literally just that she had the word admin in her job title.
And they were just pattern matching strings, and
yeah,
not
they just had a
tricking
regex that was looking for admin, and didn't have the $sign terminator and stuff like that. And it's just full of that. Now these things that are building on it now, these mesh networks and so on, they're much more professional, and they've thought about a lot of that, and they're compensating for a lot of that. But they mostly still have X509, stuck in there pretty deep, and so you're going to have to update for every X509 parsing issue that comes out.
I feel like revocation is kind of where you sold me on this. Like you wrote a long thread on Twitter about your mTLS gripes, which I am going to shamelessly plagiarize in a blog post at some point, right? But like we had written like a blog post kind of cataloging different inter-service authorization things, and we said fond things about mTLS, and you said unfond things about mTLS on Twitter, right? And like I think going into it, I might have been prepared to put up a fight, and then you talk about the revocation thing, and it immediately clicks for me that like the revocation stuff in TLS that we're familiar with and that we talk about is not the same problem as like inter-service revocation, or even any kind of like API revocation, right? Like they're just different problems, right? Like when we talk about like internet scale revocation, we're talking about generally targeted attacks or specific misissuances and things. And like there's a sense in which that system kind of converges on correctness over time, and you kind of hope things shake themselves out. And anyways, any attacker that's going after that system, like they're a passive adversary that has control over traffic anyways and all that. But like in API authentication, you have to be able to revoke. Like, there's no not revoking, right? Like, you lost a credential. Like, if you can't revoke it, then people can keep like forever using that credential. Like, the system permanently loses security. And I feel like I look at like how these systems are built, right? And I get the sense that they think that they're drafting off of a lot of security that TLS has that TLS never promised to provide, right? Like, there was never a notion that TLS was going to solve, fine-grained, immediate, real-time revocation the way that we expect, even like OAuth or something to do.
Yeah, revocation has always been the stickiest problem in TLS on both sides for client certificates and for server certificates. And there's some genuinely hard problems in there, and maybe there are better ways to solve it outside the TLS kind of ecosystem. We did for our inter API or inter service auth that we designed for AWS. We decided to do everything at request level, right? We authenticate every specific request. So in TLS, you're authenticating the channel, right? And then you're just blessing the channel, and anything that happens over that channel inherits the auth. And that means you can't authorize and authenticate specific transactions at the same time.
Yeah.
Which, we just feel is a very weak security model. So we just go for it at the request level. And then we have uncountably large sets of identities and credentials. We issue very ephemeral identities and very ephemeral, session credentials that can last seconds, hours, and so you could never even try to do something like that with TLS. Some you can kind of try by baking in epochs. You can kind of short-lived credentials and say, well, this expires at a certain time or past a certain epoch, but that doesn't give you the ability to revoke on demand. And also, if you're able to isolate something, or if you're able to influence time, and often things are just using NTP for time, you can overcome that too. So it's full of all these little gotchas. So we just kind of went, no, do everything at the request level, and we're just going to use HMAC and symmetric keys and go at it that way.
Yeah.
So let's say, though, like, just to play the other side a little bit, like, if you are authenticating on every request and you have revocation, that means that, like, more or less you're doing like a revocation check on each request. And so is there any reason that you couldn't just do OCSP on every TLS connection? Like, you're paying the check every connection cost either way, so why not just pay it in TLS?
Yeah, so we don't quite do a revocation check on every request. Instead, we kind of do proactive full lifecycle management of every credential, right? So you when you create a session credential, you push it out there, right? And it gets to the places that can authenticate. And when you want to validate or revoke it, you do the same thing, right? And there are some, fallback safety measures. If something becomes isolated, it knows it's isolated and stops serving requests and so on. But in general, it's a live, positively acknowledged feedback system, which is really, really important, right? Because if you're making changes, right, like you don't want to use a new identity or credential until you're sure everything that could authenticate with it has it, right? And in the opposite direction, you don't want to stop using one until you're sure it's no longer in use, right? You don't want to kill it unless you're like, sometimes there are cases like, let's say one of our customers has fired an employee in negative circumstances. In that case, they do want to, break their access very, very quickly. And you can do that. But if the system's pushing things, in general, it's not having to go do checks. So you get efficiency and you get the management too.
I feel like there's stuff worth thinking about in the channel versus message thing as well, right? Like, probably one of the most important kind of server-side attack vectors right now, or I'm like a year out of date because I've been doing just pure software engineering for the last year. But like when I stopped doing assessment, like one of the major things that was like, important for server-side, like when we were doing assessments and stuff, was things like SSRF. Things where you have like, an existing channel and then, just be able to send a message over it. It's counterintuitive, right? Because like you wouldn't imagine that just being able to turn a server application into a proxy would be that big of a deal. Like you can get a proxy anywhere, right? But like if you've got a trusted HTTPS channel, that it's already trusting and that anything that goes over it is blessed, right? Then you've kind of got game over anytime anybody gets a way to slip a message into that channel. And you don't have that problem with like SIG-v4 message authentication or stuff like that.
Correct.
And I think probably DSync is probably even the newer kind of form of that, right? You can imagine a DSync issue if it occurs at one of these proxy layers that's using mTLS to bless the channel. We'll have that issue in a way where an authenticated request will not.
I'm guessing that like James Kettle hasn't tested that yet, because no one's really testing Envoy and stuff for like, you can't write a scanner, or you can't make a burp plugin that doesn't. I'm saying this, and somebody's going to point out that it exists, right? That's a smart thought, right? Like there probably is something there.
Yeah, that's probably potentially a target-rich environment, but I mean, we came to it from that perspective too, right? Like there's all sorts of ways you can end up breaking a HTTP request and putting strings in places they shouldn't be, and bad escaping and so on. And so let's be more defensive there. But the other one we were thinking about is, well, we want to be able to target things like banking apps and financial customers and so on, where they literally want to sign the specific transaction and sometimes even want to sign it offline because they're very paranoid with their keys, and it's very hard to do that with mTLS.
So
go, Dave.
Tom, go ahead. I was going to move us to a different search case.
I was going to do the exact same thing. We should leave this on the edit so people can see how the sausage is made. Don't do that.
They can see how the sausage is made, so to speak. Right. So let's say you sold me on why you shouldn't use mTLS for like microservice authentication. But what about in like a kind of employee or device authentication or like zero trust scenario? But let's say SSH to make things simple. Like, let's say I have servers, then I have employees, and while you can certainly make the argument that nobody should have SSH permission in anything, let's say you need that type of permission, and you're like, okay, what I'm going to do is I'm going to build like a key vending machine that's going to give out client, that's going to use my organization's SSO to give out SSH client certs, and then people will authenticate to whatever server they want to using this client cert. And that way my config management only needs to push out the verification cert for SSH. This also kind of gives me a little bit of an edge in the argument, since SSH doesn't use X509 certs. And like you don't need to explain to me why X509 makes things complicated. But like, what about a scenario like that is an API authentication? Are client certs just fundamentally broken, or can they be used in other scenarios?
I don't think client certificates are fundamentally broken. I think PKI, is useful. And SSH is an example where it is useful. I've definitely seen customers build setups like that, although maybe they're not as common as they should be. Most people are still just using, either SSH passwords or just generating a public key and dropping it on their box. But you can, I think a lot of my arguments against mTLS fall away in that case, because they're no longer, you're no longer just trying to create this like TCP compatible, pipe or tunnel that almost anything can run over, and you're just going to ignore, the context of that protocol. SSH is very coupled, and they've really thought through how very carefully, the implications of public and private keys and how that impacts the protocol and how that affects things and so on. And I think there's all sorts of other great uses of PKI systems for building, identity frameworks and giving people, long-lived identities. Sometimes it's really the only way to do it, like with physical cards and so on, if you want to be able to work with systems that work like that, and they definitely have their place.
I guess like I might stick up for it in, I might stick up for mTLS itself in a couple of scenarios, right? Like we use some of the HashiCorp stack at Fly, right? So there's console in the mix, and there's some Nomad in the mix for us, right? And HashiCorp is really big on mTLS authentication for things. So I think Go programs in general are mTLS positive, because Go makes it pretty straightforward to use client certificates, right? And in those settings where I'm basically expressing what is sort of kind of a network topology to begin with, like the relationships there change with my network topology. But there isn't a whole bunch of like issuance going on and stuff like that, right? And a thing I kind of like about it, as opposed to like fine-grained request authentication, is that if you don't have the client certificate, like if you don't have the root secret for talking to the service or whatever, you can't talk to it at all. You're just like kind of locked out, right? And that's a thing that mTLS does that I do kind of like, right? It's similar to SSH, I guess, too. If you've turned password authentication off, then almost everything that people write about SSH hardening goes out the window as well, right? Like unless you don't trust the SSH key exchange and stuff, which hasn't been broken in forever, right? Like, I do sort of like the idea of, really coarse-grained kind of, access control rules expressed with mTLS. You could tell me I'm crazy about that. You should, by the way, if I'm crazy about that, tell me that I'm crazy about that.
Well, I've definitely seen it fail open more times than I've seen it fail closed, where people, just stand up a web server, think they have mutual auth working, and it turns out they don't. But the Go ecosystem is much better at that. It's way more explicit. I can, it's harder to get wrong than an Apache config or an Nginx config, where it's really, really a pretty intimidating recipe to make sure this thing's actually turned on.
Yeah.
But so that part I agree with. I mean, at that level, it's kind of logically identical to a VPN, right? It's, and sometimes VPNs make all the sense in the world too.
So we were talking before we started recording, and we were talking about like roughly what we were to talk about. And you slipped in right before we started recording that if we put you on the spot, you might try to make an argument that AES CBC was more secure than AES GCM, right? So CBC is like old school AES. It's how like AES protocols were designed. It's how block encryption stuff was done since like the 1990s, right? Where in particular, you separate out the encryption part and the authentication part. You kind of compose them from primitives kind of generically, right? And GCM is like, it's like a Formula One car, right? The whole thing is just hermetically sealed around doing both authentication and the bulk encryption at the same time, right? And like, I think a lot of people like GCM. I'm not a big fan of GCM. It seems really brittle to me, but I am a fan of AEAD ciphers. Like, like I would use like, Cha-Cha on Poly 1305 or something like that before I use CBC. I guess I sort of see where you might be coming from on that, but like make the argument, convince me that I should use CBC.
Oh my God, you give me two things to argue against there too, because I'll have to get back at you about AEAD as well. But so TLS kind of famously got AES CBC the wrong way around, right? There's you can't use AES CBC on its own. You have to couple it with some kind of authentication algorithm or a MAC, right? And TLS uses HMAC, but it if you give it a plain text, it would do the HMAC first and then encrypt the HMAC, which is the wrong way around. That's not what you want to do. It means somebody can, now means the ciphertext is malleable. Somebody can mess with things and try to do experiments. And we got security issues out of this, most famously the Lucky 13 security issue, right? Which Kenny Patterson and co found, which is awesome. And showed us definitely don't do it that way around. Now you can use it the other way around securely, right? If there was a cipher suite defined that, when you're decrypting, check the HMAC first and then decrypts it, I don't think anybody out there would actually would have any standing issues with AES CBC except maybe performance. It's not quite as performant as AES GCM. But AES CBC has like a lot of positive properties that if you're thinking from the perspective of like a real world attacker, somebody who might really try to go at your protocol, it's really defensive. The biggest one is if you screw up in how you generate your initialization vectors or nonces, which are just these things it takes to encrypt with it, it's much, much more defensive of that. In fact, GCM can break wide open in a way where you'll be able to forge information. And secondly, it gave us a measure of length hiding that I think was really important. And so, the cryptographic research community out there, their job is to advance the art and think of, the next cool break in cryptographic protocols. It's not to defend real world systems from real world attacks, right? And it's staggering to me that the most practical attack on TLS to this day is, well, if somebody's passively tapping traffic, whether that's, shared Wi-Fi or whatever, they can see the length of all the information that's going by and the rate of the information that's going by, right? Just classic traffic analysis stuff. And any measure of length hiding helps protect that. And there's like real practical attacks here. People have done research. They can see, what map you're looking at in the browser because they figure out the mapping tiles, or what video you're watching on a video streaming service because they figure out the size of the movie segments. Or, if you're pushing VoIP around, you can, just watch for the silences and the breaks and figure out what speech patterns are, right? And most ordinary people would be really surprised to learn that. And be really surprised to learn that like these encryption things don't actually protect their information in that way. And at the same time, most cryptographers would be surprised to learn that they are surprised. They'll be like, of course you could do that. And
just to make sure that I'm tracking this, I think I am, right? You're getting the length hiding from CBC because CBC is padded. Because when you put together a ciphertext with CBC, it's got to be a multiple of 16 bytes long. And if it's not, you fill out the balance with garbage.
Exactly. And it's a relatively minuscule amount of padding. Like I prefer a much larger amount of padding, and now TLS 1.3 has support for larger amounts of padding, but no one's using it yet. But it's even that 16 bytes, it's actually really effective at hiding the URLs, right? Like when you think about trying to analyze a HTTP session, you've got two attempts, right? You've got the size of the request and the size of the response that you can use to try to fingerprint what's going on. And it really makes the attacker's job much, much harder on the request side because a lot of URLs will collapse into that same 16 bytes. And this stuff has, it increases attacker difficulty by many, 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 many factors, and it's just a shame to lose that, over, like it's like we're not. Yeah, it's like we're not thinking through the perspective of like, but sit down and try to do a practical attack on TLS. What would you do? It'd be something like this. And it's like, well, we actually went backwards a bit on defending against that, which is just kind of perverse. It's just a little weird.
So my instinct there is that the block cipher mode or an authenticated encryption with associated data mode is like, it's at a different level of abstraction than HTTP over TLS, length extension, or, length observability attacks, blah, blah, blah. Like, if you are designing your block cipher mode or your AEAD, thinking about that, like, are you kind of like, are you out of your element? Are you like, are you going to try and shove too many sort of things into your thing that you're designing at a far lower level of abstraction of the primitive or quote unquote primitive that you're designing? Or they are basically, should you consider that? Because I don't know if CBC mode was ever, I doubt it was designed with that sort of security when integrated into a higher level protocol in mind. It just was a happy accident, basically.
Yeah, it was definitely accidental security. So I definitely think padding should be part of the AEAD kind of API, and myself and Shai Guran designed an AEAD spec 2 years ago called Scram about for AES, and we put padding right there front and center, so be in the developer's face. You need to think about how much padding you should have, right? And here's why that matters. You see it ill-considered, in a fair amount of applications and protocols out there where folks really haven't thought about, just basic blinding information to attackers. So I think we have some more work to do there. Okay. But you can't put absolutely everything a developer has to think about in the AAD, fingerprint either.
Hey, David, you've got your name on some TLS papers. How convinced are you?
I mean, I've been generally skeptical of most like timing type attacks. I don't know about traffic analysis as much. Most anything that falls under the side channels. As to like what is revealed there that simply like existence of the connection doesn't reveal. there's spots where it's like clearly terrible, right? Like the old Dawn song at Berkeley and SSH with the whole keystrokes on the password thing that from back in the day, right? That's clearly an issue. I believe that like many audio formats might leak this type of stuff, but and a lot of those are like SSH, for example, has like specific things in the implementation to avoid the keystroke timings. And I believe that like even if you have the 16 bytes of padding in audio, you might still need to do things like that. So I don't know. I was never much of a timing person. I agree that, you know, anything you can do to mask lengths and mask stuff is positive. You see this with the censorship resistance stuff a lot more, that just like anything that can be used as a side channel and that does get used as a side channel. And sometimes like really silly stuff. And sometimes, or even just the attitude of like, well, surely they'd never block AWS, and then they like block all of AWS type stuff. So I don't know.
You're bothering me. How seriously do I need to take the SSH keystroke timing thing? Is it to the point where like if I'm using
that was fixed like 20 years ago?
Well, right,
sort of.
But it's implementation fixed, right? Like, but if I'm using some random, you know, SSH library in a memory safe language where like I trust the crypto, but like there's a whole bunch of other things you have to think about when you implement SSH. Is that one of them? Like, do I need to look for that?
That's probably the first one you should look for. I say this because like I'm tangentially involved. I'm involved on the transport crypto side, not the SSH side of like a kind of SSH reimplementation, for reasons. But I don't know. I would believe that I haven't checked this in the Go one, but I assume that the Go implementation does this correctly because Go has a lot of smart people that worked on that. And like, I personally wouldn't touch drop pair with like a 10-foot pole, regardless of the keystroke timings. And that's about all of the SSH implementations are SSH, drop pair, and
literally
maybe
as
one other one.
my
Basically, I
gosh.
mean, I wouldn't touch anything that's not OpenSSH or the Go one is my answer to you.
Okay.
literally as you say this, I'm remembering that I wrote our own SSH implementation for Fly, and I didn't go look for this. And
But
it's also it's like it's
it
an X.
imports the Golang /X one, which is like the same thing that.
Okay.
that
Yeah,
I'm
but
doing.
it's an X library. They're not the same. We need to bring Filippo
Well,
on like right now.
Yeah.
Just
Wait,
Filippo.
you got to watch out for the CLI utilities, though. That's the problem, right? The way it works in SSH is the second you go into line buffering mode, right, or password input mode where you get the asterisks, it tells your terminal over SSH to like not send the input until the current return, right? And but if somebody writes an application that doesn't go into line buffered mode but accepts a secret, like it's game over, and you still see those.
You can distinguish
I've seen
it.
that. I've seen that in ostensible secure messengers before, where they send real-time updates, like who's talking, like somebody is typing, but like every time they type, like you get like fine-grained messages, like when the keystroke actually happens. And I always wonder like how crazy that is. Like, you know, you probably want to do something to like debounce or jitter that or something like that.
Yeah, I mean, I saw stuff back in like 2014 of like, you know, just figuring out what you typed just by listening to it. So like,
Yeah. I hope that would be
I'm sure
fixed.
it's not great.
Coming back to CBC or other AADs, I think that if you came up with another AEAD and was like, hey, it's all padded so that you can't distinguish lengths, someone would be like, it should be secure without all that extra padding, you know, blah, blah, blah. Why is it so fat? And it would be harder for you to like get support for your thing if it was you know, thickly padded, even if it was to mitigate exactly this kind of attack when it's used in a higher level protocol.
I mean, we saw like exactly this with like AEADs the first time around. We can go and look up that email from why am I blanking on his name? The moral character Phil Rogaway from like
Yes.
1996.
Yes.
Where he's like, you motherfuckers are fucking all of this up. Like, you would never say that. He's like one of the most timid people, but that's what he's saying.
He's a really
He
nice.
basically describes everything that goes wrong in the next 20 years right then. And then they're like, but
performance,
Okay,
or like,
so-
and this isn't realistic.
So
Or he's just saying
clearly-
like use the AEAD abstraction, which like he had basically just come up with at
And
the
then
time.
like 20 years later, everyone comes back. We're like, we're sorry. Can you like release the patent on this? We really want to use it.
Yeah. Or same with like, let's build custom block. Like we have custom block cipher mode specifically for disk encryption because that's a separate problem. It doesn't seem unreasonable to me to want to have a separate block cipher mode or AEADs that are designed for length hiding to be used in transport layer encryption.
Okay.
I know, like,
that doesn't, like that
know-
seems reasonable to me.
I know the thread that you're talking about, right? That's the one where like people were referring to Phil Roggeway as like a so-called cryptographer when he was trying to fix IPsec. All I have
Yeah.
to say about this is that obviously the next time we do a recording, one of the things that we need to do is a dramatic reading of that email with you as the anger translator. I'm not kidding in the least. It'll work.
Yeah.
It'll be great.
Yeah,
Well,
we can get we can get the Jason on for WireGuard and do that.
yeah.
I have just like one more question for you, Colm, which is, in a day that shall live in infamy, on this podcast, we had Ryan Sleevey, who is one of my personal heroes, and I kind of with some hubris brought up DNSSEC and asked if it was okay for us to stick a fork in it and declare it dead. And he gave a whole speech that has shaken me to my core for the last 2 weeks about how what they're doing in Europe with certificate authorities means that there is a future for DNSSEC, and in fact, we may be soon in a Dane world. And I'm not even asking you a question so much as making a request, which is, would you say he's wrong, please?
And it's important to note that that request was not individually authenticated. We authenticated his transport connection first. So
Sure. I think DNSSEC it's probably best described as a zombie right now. In it is the living dead, and I say that with a twinge of regret. I think at this time, at this point, I feel like DNSSEC is mostly being propped up by regulation. At least the folks who I see using it tend to be the folks who have government mandates to use it, or ICANN mandates to use it, and which I guess is just another form of government. And it isn't getting too much commercial adoption. And I'm kind of skeptical of the protocol's fundamental future, just because it seems really poorly positioned for like the next round of updates or break. It's really, really hard to update the parameters in DNSSEC. Very, very slow. Some of that's due to the nature of the protocol and just how crufty all the things out there that support DNS are. If you think that the challenges that Greece had to overcome in the TLS space are anything, they're 10 times harder in the DNS world, where there's all sorts of very old DNS implementations out there that really can't handle any changes.
Yeah.
And things will come along and updates will have to happen. And what are folks going to do? And then the other part of it is there's not much of a deep technical community around it who are able to steward and shepherd all that. TLS has a really deep bench of folks who work on that, who go to work every day, and that's their job, and they keep the world moving on that stuff. And DNSSEC doesn't really have that, so it's really hard to see it kind of thriving. At the same time, I don't want anyone listening to think we don't stand over the DNSSEC or mTLS implementations we have at AWS. We support these things, and we put a lot of work into getting it right for people and making sure that they work really, really reliably. But, these broader ecosystem concerns are real too.
I feel like you hear sometimes like a thing that gets brought up with DNSSEC a lot is that like the ecosystem as deployed right now is mostly RSA 1024. Like there were like recommendations to use 1024 for like the mainstream keys, and then the longer lived key signing keys can be like 2K RSA keys. But like the obvious criticism is just it shouldn't be RSA at all. It should be curves. And then people will point out, well, there is curve, DNSSEC, right? Like you can use the P curves with DNSSEC, and Cloudflare has an implementation of P curve DNSSEC. And it's like, there's like two problems there, right? The obvious problem there is that P curve DNSSEC is like, 1990s curves. But like the other problem is just like none of the deployed, the actual deployed base of TLS or of DNSSEC is P-curve DNSSEC, right? Like you imagine how long it would take to get that stuff deployed, and it's, you know, it seems like it'd be an eternity to get that to actually happen, let alone getting like curve 25519 or something like that deployed.
Yeah, and it's been at least 10 years just to get 1024 out there, and that's gone pretty slowly. I don't even know where you would start on if you wanted to really deploy EC, and you'd have to turn off RSA as well, really, to get the security benefit.
Yeah.
Like it's really 2 steps, and getting to the end of those 2 steps, I mean, at the current track record would take over 20 years. So that's why I'm skeptical of it. But, you know, it's a protocol. It's got security in the name. Folks are gonna, you know, want that extra comfort of using it too sometimes. And at least we're getting better as an industry of avoiding outages and you know, operating it very well. We're starting to see more mature implementation show up that, you know, safeguard against that. So it makes it kind of, there's less downside to using it than there was before.
I feel like when Ryan was talking, by the way, I've begun everything I've said this time with the words I feel like a lot of things today. But like when Ryan was making his case for this, I think I should have been more forceful. And I think you're seeing me attempting to be more forceful about my dislike for DNSSEC right now. So what I'm hearing is it's a zombie, so you can stick a fork in it, but aim for the head, so it's dead permanently.
Well, I personally would love to see a revived effort to have a real, you know, secure DNS protocol. I actually think if you step back from the internet architecture and you were doing everything afresh, right, you would want encryption to be like a day one property, right? You'd want it to be right in there, and you'd want it to be part of the name lookup, right? You kind of want everything that happens in DNS and everything that happens in the TLS handshake to be one protocol, right? And you just you start with a name and you get back an IP address and a key, right? And maybe a port, whatever. And then you go connect to it and you're good, right? And doing that well with, you know, confidentiality and privacy, which DNSSEC doesn't have, with with full verification and authentication at each stage would be really, really awesome. Like there's definitely a space for that. And hopefully we'll see it at some point.
You're starting to see it bottom up with things like DOH, right? But like if you step back and look at like how this came to be, right? What you're really just seeing is like sheer bloody-minded path dependence, right? Like we're working with the constraints that a small DoD project had in like the mid-1990s, where like it's not encrypted because they felt like DNS servers of the time wouldn't be able to keep up with encryption, right? And there's a notion of offline versus online signing where like the protocol can't, you know, make any nods to online signers, like, you know, anything that actually has a key and can do cryptography in real time. Because, I mean, you can make a message board argument that that's a good property, but the reason it's there is because they felt like the systems of the time that were going to, you know, when DNSSEC was fully deployed in 1997, or whatever the plan was, right? Like that, like those servers wouldn't be able to keep up with it. And we need a protocol that's designed around 386 SX, you know, DNS servers or something like that, right? I totally, like, I buy completely, like, I come across as an evangelist for not securing the DNS, but I think DNSSEC gets in the way of securing DNS.
I agree with that, and I think I'm optimistic that we can solve all those technological problems and challenges. I think there's another property too, though, which is maybe speaks to your other concerns about DNSSEC and PKI about, you know, they can be subverted by single parties sometimes, right? Whether that's a DNS operator somewhere in the tree or a rogue CA or whatever, right? And I think stepping back, you kind of look at it and you go, well, wouldn't you love to just make that a multi-party system where, you know, everything has to be signed by end parties, and that's computationally cheap now, and we can have many CAs now and so on. But that's that kind of change where essentially everyone becomes dispensable, right, by design. Those are harder to do. So the kind of changes you're ambitious for, I'm less optimistic about.
So you're saying it's a coin.
No, I don't think blockchain is the answer.
You said secure multi-party computation, and I'm like, you have Deirdre's attention, so.
Yeah.
Sure.
Do I have to write another threshold signing protocol?
I'm not even talking about threshold signatures here. I'm just talking about, you know, you could have to say, you know, something in the DNS or a certificate, right, just has to be signed by multiple parties, right? And then you could just have the
Multi-sig.
software. Exactly. Simple as that, right? Would be another interesting change.
Well, Colm, thank you so much for coming on our little show. This has been great. Anything else?
No, it's
I
been
got
great
nothing.
too.
Cool. Awesome.
Colm, it's great. It was awesome to finally meet you and talk to you. Thank you so much for taking the
Yes,
time.
thank you.
Thank you all.
All right, I'm gonna stop recording. It's gonna